All right, we can get started. So, want to welcome everybody today. Thank you for coming to this, the first of 9 of our full spectrum series. We're doing these so that students can get a sense of the different fields within the Hajem School. We're going to do each major, and we're also going to do material science. We're going to do data science. So, we're looking for students who are interested in the multidisciplinary part of engineering, but also students who may have started in a different major and think, hey, maybe I want to come to a different Hagen major, in this case, mechanical engineering. So we're very, very pleased to be joined by Dr. John Lambropoulos. Professor Lambropoulos is a professor of the Department of Mechanical Engineering and also in material science. So Professor Lambropoulos, the floor is all yours.
Okay, fantastic. Thank you, Nick, very much. Again, welcome everybody to this presentation. I'm sharing my slides, and you will notice that the data for this presentation, July 2020. So I gave this presentation a couple of months back, so I will sort of repeat the presentation. I will make some additional comments in the meanwhile. As a point of introduction, I will also mention that, that 2 of my children have graduated from U of R a few years back. And both of them are very gainfully employed in what I would call high technology kind of areas. So I've had the opportunity to see the university both as a parent and of course as a teacher. So basically, what is mechanical engineering? Mechanical engineering is this combination of structures, materials, fluids, energy, and power, with an overall theme which makes engineering, including mechanical engineering, very different from what we call the traditional areas of science, like biology or chemistry or physics or geology, environmental sciences, and so on and so forth. I would also like to emphasize that, as you know, of course, you will see in the top of my slides that I have this cascading list of affiliations. So, of course, we're at the University of Rochester. The college, essentially the undergraduate enterprise at the university is within the university. The Hagen School of Engineering and Applied Sciences within the college, and our Department of Mechanical Engineering is part of Hagen. Therefore, I like to think of our department as part of a large research-oriented educational institution, and a lot of the comments I'll be making will be in reference to this overall structure. Oops. So the essence of mechanical engineering. First, as I mentioned before, mechanics and materials. So here the basic question is, why do structures fail? Why do things fall apart? Maybe you read this morning on the news that there was a very scathing report from the Federal Aviation Administration on the very poor design execution of some of the issues related to the Boeing MAX aircraft. Essentially, we want to make sure that the structures will not fail. They will not fall apart. Of course, in order to do that, we need to understand what failure actually means. One important part of mechanical engineering is dealing with fluids, energy, and power. So by fluids, energy, and power, we mean things like how do I produce propulsion? How do I make a car move? Or how do I make an aircraft move? How do I make a satellite move? How do I make a rocket, a SpaceX rocket actually move? Traditional fuels, usually petrochemical fossil fuels, but also alternative energy. That's a very big part of mechanical engineering. But the most important part of what makes engineering so different from the sciences is this notion of engineering design. And by this we mean, how do you make a gadget? How do you make a device? How do you make a structure so as to accomplish a given goal, a given objective? And just to give an idea, this is a very open-ended, very unclear question. And just to give you a sense of how variable the answers on this may be, think about, for example, the design of cars. You could have a small, inexpensive car. You can have a large, expensive, perhaps inexpensive car, anything in between. They all execute a certain function to transport people and stuff safely from one place to another place. But how we go about designing one car as compared to another car is what makes this notion of design a very open-ended kind of exercise that is a very integral part of the undergraduate engineering curriculum here at the university. A very big part of engineering design is what I call virtual design and simulation. Namely, if I have an idea for a new car or a new aircraft or a new smartphone or a new tablet, whatever, for a new chair for that matter, whatever, I don't actually build every new idea in the laboratory because it's too expensive and too time consuming. Instead, what I do, I build virtual models of that device and I virtually test the device by simulating its performance so that I can gain some valuable design information in addressing the overall design problem. A very big part of mechanical engineering curriculum is there's extensive hands-on project work and experimental work in laboratories. And perhaps most importantly is that engineering is not a hermit's kind of job. Engineers always work in teams. Therefore, we train our students to work in teams. And of course, working in teams means that we must be able to communicate with each other. As a matter of fact, I would say that the most important skill that successful engineers possess is not so much the technical knowledge. The technical knowledge will make sure you have it, but the ability to communicate successfully with your colleagues, with your supervisors, with the people who report to you, and also to work effectively, constructively in teams. That's a very important skill that it takes some effort to actually develop. So we include this as part of our undergraduate curriculum. Now, I've listed here this is actually quite an old study. This is a 17, 18-year-old study from the National Academy of Engineering, which lists the greatest engineering achievements in the 20th century. So the 20th century is the last century. And I've highlighted here in red the important contributions that mechanical engineers have made in these last 100 years, providing electrical energy and distribution, cars and related technology, airplanes, water supply and distribution, agricultural machines, air conditioning and refrigeration, design of highways, design of spacecraft, household appliances, health technologies, a lot of energy-related petroleum, petrochemical technologies, nuclear technologies, and high-performance materials. So these are, as you can see, that more than half of the greatest accomplishments in the last 100 years have big contributions from the mechanical engineering discipline. Now, of course, we may want to when we look at. Let me go back here for just a minute. Now, students participating in this Zoom presentation might be wondering, yes, but now we're not in the 20th century anymore. Now we're on the 21st century. So what I will do is at the end of my presentation, I will give you the similar list of the top 20 greatest challenges for the 21st century, again, from the National Academy of Engineering. Now, again, I mentioned that a very important part of mechanical engineering is designing. And in order to design, I need to make sure that something is as optimal, is as good as possible. I want to optimize a certain performance. And we do this by looking at different, what we call performance indices, and we want to maximize this. So we need to deal, first of all, with technical performance. I want to meet a certain number of technical specifications. Cost, of course, is very important. Safety, of course, is very important. Environmental effects are very important. Sustainability effects are very important. When I look at environmental effects, by environmental effects, I understand things that can change on the order of 5 to 10 years. In other words, if we do changes in our engineering technology, we can have an environmental impact within 5 to 10 years. On the other hand, if I look at changes on the order of 50 to 100 years over several generations, then we're looking at sustainability type of performances. And the way we do this in engineering is to quantify everything. Engineers like dealing with numbers, we deal with quantities. For example, if I need to optimize for a certain technical performance, there may be weight, whatever that may be, that needs to be maximized. If it's for I want to is the cost of the product. I'm actually for the environment again, 10-year type of horizon. I need to be concerned with how much, for example, with how much electrical power I'm consuming when I produce this kind of design, and so on and so forth. Why? Because electrical power needs essentially the burning of fossil fuels for its production. On the other hand, from the point of view of sustainability, again, on the 10 to 100 years type of time horizon, we're looking at certainly I want to optimize my technical performance, but on the other hand, I want to minimize solving the CO2 problem, essentially leading to global warming. I need to minimize that, and solutions to minimize CO2 production cannot be done on the order of 1, 2, 3, 5 years. These are long-term solutions. So we look at this as being sustainability type of solutions. Now, one very important part of that, a big, if you like, a big overriding theme in all aspects of engineering is professional ethics. And we need to realize that I don't think that any of us, faculty, staff, engineers, any person, if you ask a person, are you ethical or not? I don't think there's a single person who will say, I'm not ethical. Everybody thinks of themselves as being ethical. But the point I'm making from here is that when it comes to professional ethics, ethics related to the practice of engineering, professional ethics are more detailed, more nuanced statements that we need to think about explicitly when we work as engineers. For example, as I mentioned before, in mechanical design, we need to optimize the performance of our gadget, the performance of the smartphone, the performance of the Boeing aircraft, of the Airbus aircraft, the performance of a chair, of a table, so on and so forth. But of course, all engineers have this ethical responsibility. So one question that I always like to pose to students, this is a very simple question, true or false? The question is, the statement is, engineers in the fulfillment of their professional duties must carefully consider the safety, health, and welfare of the public. So this statement, I don't think that anybody will say, if I work as an engineer, or if I work as an administrator, or if I'm a politician, nobody will say I'm unethical. No matter whom we ask, every person thinks of themselves as being very ethical. But if we think about the statement of described here at the bottom in black, is this statement true or false? And it's not clear whether the statement is true or false. As a matter of fact, when I've given this question to undergraduates, to second or third year students at the University of Rochester, most students actually fail this question. It turns out that this statement is false. And it is false because it says that engineers, pay attention here to the verb, engineers must carefully consider the safety. And of course, the point being made here is that engineers must not carefully consider, but must hold paramount the safety, health, and welfare of the public. Therefore, it is not sufficient to say, I will carefully consider the safety in designing a Boeing MAX 200 people kind of aircraft. Carefully considering something doesn't mean that you will actually do it. Carefully thinking about something doesn't mean you will actually do it. Therefore, one of the most fundamental tenets in the list of the ethical responsibilities of the engineer, the professional responsibilities of the engineer is that the engineers in the fulfillment of their professional duties shall hold paramount the safety, health, and welfare of the public. Not just take it into serious consideration, but instead it's safety, health, and welfare of the public is the single most important factor in the design. It's not cost. It is not whether you'll keep your boss happy. It is not whether you'll get promotion. It is not whether you're going to demonstrate how smart you are. The single most important thing, the safety, health, and welfare of the public. I will give you some examples of what engineers have been doing over the years and why mechanical engineering is such an important discipline, engineering discipline, designing energy efficient homes. And I will show you from here that clearly this is a sort of what I call this looks like a pretty nice home. It looks beautiful, with a lawn, several stories, and so on and so forth. However, I need to make sure that this building is warmed properly. It is cooled properly and efficiently without having too many losses. Therefore, the design of thermal insulation, that's a very important part of mechanical engineering. I will give from here one example. A refrigerator. Everybody knows what a refrigerator is. It's a very common household appliance. You'll see from here how the electricity use in refrigerators has dropped from about $1,800. I'm sorry, from $1,800 kilowatt hour per year to about 300 over a period of 40 years. Therefore, the point to observe from here is that the efficiency of, let's say, household devices, instruments, implements, has improved tremendously as a result of mechanical engineering. I will give from here some examples of this, again, stuff that we actually teach to our undergraduate students in mechanical engineering. Essentially, the distinction between power and power. There's power and there's power. For example, in a very traditional so-called coal-fired steam plants, an example of which you will see right here in the middle. Essentially, we have a steam turbine. Typically, a steam turbine cannot operate to temperatures higher than 650 Celsius or so. And it turns out that if we have a traditional steam power plant which produces electricity, no matter how smart I am, no matter how hard I work, the efficiency cannot really be made better than about 30%. In other words, there's something inherent in using steam as my working fluid that limits this efficiency to about 30%, 31%, and so on and so forth. On the other hand, if instead of having a water-based power plant, if instead I have a gas turbine, for example, using air as my working fluid, now the efficiency can go up to 6%. The reason for this is that if I can operate at much higher temperatures, the efficiency improves. So this is a very fundamental principle in mechanical engineering. Why is it that if I can operate at higher temperatures, my efficiency improves? So there's something very fundamental, very profound in this statement. Of course, in order to actually do that, I must make sure that I can design materials that can withstand temperatures to 1200 degrees Celsius. Again, just to put this in perspective, aluminum at 1200 degrees Celsius, at this temperature, aluminum is melted. Aluminum cannot be used as a working material for making a gas turbine. Therefore, I have to think about the development of high temperature materials that can operate at very high temperatures without failing, essentially. I will give here one example of what I refer to as a virtual design. This is a valve train lifter. This is actually being used in a car engine. You will see from here there's a piston assembly with a cylinder. The piston moves up and down, therefore transfers linear motion into circular motion. That's how the car actually works. And essentially, this is a mechanical analysis using software that will predict during the operation of this train lifter, of this valve, essentially which parts are significantly stressed, so I can actually concentrate on whether or not failure will actually take place in that location. A parallel kind of idea is, how do I optimize the design of a structure? And by optimizing, I mean I need to have my structure being as strong as possible while being as light as possible on the other hand. Therefore, if I start from a cubic chunk of material, how do I go from this chunk? How do I machine this chunk into a bracket that looks like so? Therefore, now what I can do, I can optimize the manufacturing process so that my structure, my bracket is as light as possible while being as stiff as possible at the same time. So again, this is a virtual design. So I don't have to try, 50 different ideas, machining 50 different blocks to create 50 different brackets, test each bracket separately. Too time consuming, too expensive. Here's another example, again, from the valve train assembly analysis. This is what we refer to as a dynamic analysis. So now imagine that the car is actually moving, the engine is actually operating, so things change as a function of time. And now you will see that everything now vibrates, everything kind of shakes, so to speak. This is a car valve train assembly. It's from an automotive application. Of course, the exact same issues if you're designing an aircraft, if you're designing a satellite, if you're designing the structure of a house, a multi-story building, and so on and so forth. Again, this advantage of virtual design is fantastically important. I want to show you from here an example that on the left, you will see from here this virtual design. Again, the valve train assembly. We do the virtual design. There's a hole for gas, essentially for fuel intake. And the theory, the virtual design predicts that on the surface of that hole, something bad is going to happen. You will see from here this purple sort of alert kind of zones. So the virtual design predicts that something bad is going to happen on the surface of the hole. When we actually build the structure, you will see that this is the hole. You will see those cracks, hairline cracks that propagate from the surface of the hole. If these cracks make it all the way through, of course, this structure is actually going to fall apart. Therefore, rather than wait and build this structure, expecting it at some point to fail, I can predict its failure by doing this virtual design. So this is a very important part in our analysis. I also want to sort of show you the importance of engineering materials. I've selected here a very simple problem. Everybody knows that if I want to buy liquid, I need to keep liquid in some container. Therefore, I can use a glass container. Typically, if I buy wine or champagne or some expensive liquid, it's typically stored in glass. But milk often is in polyethylene, those white plastic containers. Soda in PET, polyethylene terephthalate kind of containers. If it's soda or beer for that matter, sometimes even wine in aluminum containers. Therefore, the question is, from all these possible containers, which has the lowest production energy penalty? Which is the most beneficial for the environment? And from the sustainability point of view, which of the four has the lowest CO2 production burden? Now, of course, in engineering, we need to be very open-minded. So I can use glass, I can use PE, polyethylene, I can use PET, aluminum, I can use something else. Nothing tells me that I can limit my attention only to these materials. And I have listed from here different possibilities. So again, PET. So this is the white plastic, polyethylene, glass, aluminum. Glass and aluminum. And also I've included here as a material a container made out of steel. And you see from here that depending on the different materials, I have listed here in red the best choices depending on what your point of view actually is. For example, in terms of how much my material is actually going to weigh, if I use polyethylene, essentially the milk container, the milk jug container, this is a very light structure, and so is the aluminum structure. On the other hand, if I look at how much energy I need to consume to make that container, PE has a very low energy cost, but aluminum is an energy hog. Producing aluminum is very energy intensive. So aluminum is good in terms of weight, but it's bad in terms of energy content. If I want to look at how much CO2 will be produced in making this container, again, now the PET has a very low CO2 burden and PE a very low burden. On the other hand, if I'm very economic minded, if I want to see how much it will cost, say for 1 liter of milk or wine or soda or beer, whatever, the cheapest material is either PE or steel. Again, the point that I'm making is that here we have produced these quantitative matrix in order to assess the performance of different materials, and performance depends on the manufacturer. Is it a matter of weight? Is it a matter of energy content? Is it a matter of sustainability, burden? Is it a matter of dollars and cents? The point of view matters. In other words, how we actually phrase this question. Again, I just want to show you that, again, we talk a lot about in material science, which is a very integral part of mechanical engineering. We talk about the different classes of engineering materials, metals and alloys. And then we have ceramics and semiconductors. Then we have polymers. Then we have composites. And you see that the cost of these materials varies tremendously. For example, concrete, the primary example of a ceramic material, is very inexpensive. It's also quite heavy. On the other hand, diamond, as you can imagine, is very expensive. Platinum is very expensive. Gold is very expensive. But you will see from here that cost in anything that engineers build, cost eventually will come into the picture. Therefore, we must be aware of the cost of engineering designs. I've also listed from here what I call the life cycle of an engineered product. So we start from stuff we get out of the surface of the earth. I need to purify this material. I need to make my product. I use my product. Then I need to discard my product. Well, to discard my product, I have to heat it up. I have to grind it. I have to dispose it somehow. And then I can recycle the product. Therefore, when engineers think about that product, we don't think about a single use of that product, but we think of the life cycle of the engineer, of the engineered product, if you like. So here we'll talk a little bit more about the technical, about mechanical engineering. When it comes to structures, in structures, everything boils down to 4 categories, namely things that can go in tension and break, things can bend and break, things can twist and break, and things can compress and fail. And when we look at the engineering structures, we have essentially a background engineering material. It could be ceramic, could be glass, it could be metal, could be plastic, could be polymer, whatever. Then we have a macroscopic shape, a shape that I can actually see with my eyes. But then I can possibly have a material that has a micro structure to it. It could be grain boundaries, it could be defects in the structure, and so on and so forth. Therefore, when we look at engineering structures, we look at the material plus a shape. So it's the material plus shape idea that lets us do engineering design. Again, I mentioned from here that depending on how we design structures, the point of view matters. I remember many years ago, an older friend of mine mentioned to me that in engineering design, the 3 things are safety, timeliness to design, and cost. Any 2 of these can be done very easily. It's only when you need to do all 3 at the same time that the problem becomes very challenging. In other words, safety, cost, and how quickly can the design can actually be done. So I've had from here an example of a structure, how we go about designing a structure that's light and stiff. So light and stiff, think of the space shuttle. So the space shuttle must be a structure that's light and stiff, or the wing of an aircraft. Here's an example of a structure that is light and strong. So light and strong might be, for example, the fuselage of an aircraft that needs to be pressurized and depressurized over many cycles of landings and taking offs. On the other hand, if I design a commercial product, for a commercial product, I need to design something that may be stiff and economic. So for example, if I design a car, I cannot have a car whose frame is flopping all over just like a piece of paper, just like a piece of plastic. But on the other hand, it must also be economic. Therefore, I can formulate the different design requirements by looking at different metrics in my engineering design. Again, how do I formulate the metric for something that's environmental and stiff? Environmental, again, means that I should not use extensive amounts of electricity to produce it or to operate it, but my structure cannot be flopping all over the place. My structure must be quite stiff or sustainable and stiff. In other words, I must minimize its CO2 production burden. I want to give you here some examples of projects that the mechanical engineers work during the 4 years here at U of R. And I've selected those examples of courses that myself and my colleagues have taught over the years here at the U of R. So we'll go from younger courses to second year courses to fourth year courses. So in the second year example design project, to design a small water-based power plant as a backup power source for a small hospital. So this is the problem statement. Students must take into account technical performance, safety regulations, environmental regulation, of course, cost. Another example of second year design project is to redesign essentially a heating, ventilation, air conditioning system to operate with R744, which is CO2, instead of the more environmentally detrimental traditional R134A coolant. If you go to and shop at the Wegmans, as we always do, you know, of course, that the Wegmans has a very huge air conditioning and refrigeration infrastructure. And if I want to go to the cheese section, to the meat section, the fish section, you know, the beer section, a huge air conditioning and refrigeration kind of section. But if I use the more traditional R134 refrigerant, that's very environmentally unfriendly. It's actually environmentally catastrophic. Therefore, start going about 5 years ago, Wegmans is slowly changing to using CO2 as the refrigerant. And this is a great solution because essentially what you do is you remove CO2 from the atmosphere, you freeze it, you cool it, you convert it into a liquid, you use it as a refrigeration fluid so that the cost to the environment is essentially zero. That's a beautiful engineering solution. And this is an increasing solution. Just to give you an idea, if you buy a new, I don't know what car. So a couple of years back, I bought a Camry. If you buy a Camry, the air conditioning system unfortunately still uses R134A as the refrigerant for the air conditioning system. But if I buy a much more expensive, I don't know, Mercedes-Benz, and Mercedes-Benz is using CO2 as the refrigerant in its air conditioning system. So again, this becomes a matter of choice of technologies, cost, and environmental sustainability effects. But again, these are examples of a design project that second year students do in mechanical engineering. I could take this could be an exam or homework question from a second year course of thermodynamics, essentially a full analysis of a steam power plant, essentially analyzing the technical benefit, the technical cost, and the efficiency of this overall power plant. Therefore, understanding what it is in this power plant that makes it have an efficiency about 30%, that's a very profound capability that mechanical engineers will provide to our mechanical engineering students. Again, if we look at this problem from the other point of view, how do we go about designing either a refrigeration system or a heat pump system? Again, this is material that we teach to second year engineering students, and many of our students have actually gone on to get, believe it or not, summer internships working at Wegmans, in the Wegmans air conditioning and refrigeration plants, which is slowly converting to the CO2 refrigerant. Therefore, understanding refrigeration and heating is a very important part of mechanical engineering. So now we're moving to a little bit older project. So this is a third year course. This is a course that Professor Funkenbush, one of our participants, he's the dean of students at the Hayden School, and I have both taught many times in the past. As an example of a design project, is to find the best material for designing a large telescope mirror such that it operates over a range of temperatures, is resistant to vibration, and so on and so forth. And the choice of materials can be glasses, ceramics, metals, or composites. So now we're looking at what is the best material choice for a given technical design task. So from here again, a design project in the third year of mechanical engineering heat transfer course. This is a large optomechanical design project to design an optimal cooling schedule, how to best cool a large piece of very expensive glass that must be cooled from 200 degrees to room temperature without breaking. Just to give an idea, this is a piece of glass that's about it's about a meter by half a meter in size, maybe by 10 inches thick. So this big slab of glass that costs on the order of $100,000. So it costs as much as it costs to buy a house in I don't know, in Greece or in Webster or in Brighton. Very expensive piece of glass. We cannot afford to break this piece of glass. How do I best thermally cool this piece of glass? Again, this is a design project that we give to students in the third year class. One very important part in heat transfer is understanding the science of global warming. I always tell my students that there's no question that global warming is taking place. Nobody's arguing that global warming is or is not happening. Everybody agrees that global warming is taking place. The big political question is who is screwing up the global warming, so to speak. In other words, who is responsible? Is it anthropogenic or is it natural? That's where, let's say, the world and the US and the Democrats and the Republicans actually disagree. But understanding the science of global warming is essential. So we actually teach, as part of thermodynamics and heat transfer, the overall energy budget involved in using greenhouse gases and how reduction in greenhouse gases affects global warming. So this is a fourth year design project. Now we're looking at more. So these are, let's say, the senior level design projects, larger projects. One example, simulate a reactivity accident in a nuclear reactor. It's awful to think that the nuclear reactor can actually fail. But in order to prevent failure, I need to understand what might lead to failure. Therefore, analyzing the possibility of an accident is important before I have to face the reality of an accident. Another example of a design project, design a turbocharged engine for an aircraft. So now we're looking at much more ambitious, bigger projects that include a large portion of undergraduate knowledge. Another fourth year design project, design a wind turbine for a third world country. It can cost no more than $10,000, but only use off-the-shelf components. Therefore, you see from here how cost, technology, and also access to technology play a role in mechanical design. Here's another example of a senior level design project. Design the support structure for a very thin, deformable mirror so that you can actually use sunlight to cook. Therefore, what you can do, you can concentrate sunlight into small focal spot in order to essentially have concentrated heat. Now, it turns out that sunlight by itself, on an average day, if I take an egg and I leave it out in sunlight on a day such as today, no matter how many hours I wait, the egg will never cook itself. On the other hand, I can design a structure to take advantage of sunlight so I can actually cook the egg in a short amount of time. Again, engineering design. So this is an example of the mirror example we were referring to previously, where the students in their virtual design find that mirrors can vibrate in this breathing, what we call this breathing mode. So it's like think of a balloon surface that's moving up and down. It's called the breathing mode. Or you can have this double mode that's sort of it has a ridge in the middle, a valley and a valley. So how different structures shake and vibrate, that's an important capability in mechanical engineering instruction. I will give from here one example of 3D manufacturing. Again, this is a 4-year design project. The students have to design, build the prototype, and measure a trefoil mirror. And then they used 3D printing on the U of R campus over at Retner for actually doing this. A trefoil mirror is a mirror that looks like a potato chip, but has a threefold symmetry. So you can see from here, so on the left is the CAD model for the design. On the middle is the actual 3D printed. It has been coated with a very thin layer of gold in order to be able to measure the surface. This is the measurement of the surface, and then the students took different measurements across the surface to see how close to the specs the 3D design actually was. So this is a project that involved optics it involves mechanical engineering, it involves manufacturing, and it involves metrology. So it's quite a nice. This is another project again in the fourth year students to design essentially a holding a fixture for testing the glass screens of smartphones. So think of an iPhone. You have this very thin glass screen. How can I test the strength of this glass screen? The idea is that if I end up with any kind of chips, glass chips on the surface, those are killers. The glass screen is actually a goner. So this is the CAD model of the design fixture. This is the actual model, and these are observations that the students had actually taken on the design. Therefore, you can see from here how we go from designing in CAD, implementing in a prototype, and the actual testing. Something I would like to point out, I know that a lot of students have a big interest in renewable and alternative energies. There's extensive U of R work in the areas of solar photovoltaic power, fuel cells, biomass, fusion. As you can imagine, fusion is one of the huge contributions that I believe U of R is making and will be making in the near future in human knowledge. That's a huge U of R highlight. On the other hand, there's not a lot of research on nuclear energy. There's not a lot of research on geothermal or hydropower or wind energy. In a place like U of R, we cannot do everything equally well. Therefore, we concentrate on doing a subset of interesting problems, but to a very high level, to a very deep level of knowledge. I don't want to talk about sequestrating CO2 because it's students in mechanical engineering, extensive project work with a hands-on work, extensive teamwork, small teamwork, getting data, wind tunnel experiments, so on and so forth. A lot of oral and written presentations. You'll be making upwards of 20 or 25 presentations in 3 years, working in groups, oral presentation and written presentations. A very important skill that we need to teach our students on. Again, engineering design project work. You will see from here that structures made out of balsa wood. Many high school kids have done building balsa wood structures in high school, but here the catch is that this structure must first be built in a virtual model, tested on the computer, and only built if the structure has been optimized on the computer, and the students get credit if the computer projection and the actual structure actually agree. Therefore, this is a very sophisticated way of actually doing design. There are a lot of extracurricular events in engineering, including mechanical engineering, like the mini Baja competition. That's a great competition if you like cars and getting muddy and dirty and sort of need to be hosed down, so to speak, with a hose. Solar Splash, another project which is essentially using photovoltaic power for propelling a boat. That's a crazy idea, but it's a beautiful idea, right? Student teams. There's a U of R faculty members and advisor, and students compete annually. And typically, what do our graduates in mechanical engineering actually do? About 1/3 go to graduate school, about 2/3 work in industry, some going to eventually going to business school or law school. So think about how crazy is this? You get a degree in mechanical engineering, but you can do, if you go to law school, you can actually do patent law. So patent law is a very lucrative, very high in demand enterprise occupation, because you need both the legal training and the engineering training. A lot of mechanical engineers work in entrepreneurial type of small company occupations. In terms of starting salaries, those numbers may be a little bit outdated. So typical starting salary for a BS in mechanical engineering is about 60 to 65 to 70K by now. With an MS, put another 15 to 20K if you want to do that. I started my talk this morning by showing from here what are the greatest accomplishments according to the National Academy of Engineering in the last century. But of course, your century, the student's century, is the 21st century. So I want to close this talk with again, NAE, the National Academy of Engineering, presents as the greatest engineering challenges for the 21st century. So these are the challenges that the students' generation, that these are the challenges that you will have to face as professionals, as managers, as administrators, possibly as politicians, in order to solve our collective human challenges. Challenge number one, making solar energy economical. Provide energy from fusion. Provide access to clean water. Reverse engineer the brain, sort of pick and choose. Develop carbon sequestration methods. Engineer the tools of scientific discovery. Restore and improve urban infrastructure. Prevent nuclear terror. The point that I make from here is that if you look at these big challenges, it's not entirely obvious now that a topic is clearly mechanical, clearly chemical engineering, clearly electrical, clearly biomedical, clearly optical engineering. Now the problems are so multidisciplinary that we need engineering knowledge from many different sources to solve these big challenges. For example, problem number one, how to make solar energy economical. To make solar energy economical, I need to collect solar energy. This involves optics. I need to concentrate solar energy into materials. This material science. I need to make solar energy, to convert solar energy into electricity. This is mechanical engineering. I need to distribute electricity through a network. This is electrical engineering. And everything must be coordinated with software so that all the different components communicate with each other, are safe, and so on and so forth. So this involves computer science. And of course, on top of everything, everything must be done to the level of humanity, if you like. Therefore, biomechanics and biomedical engineering play a very big role because everything must be safe to a certain extent. The point that I'm making is that as you're moving into these big challenges in engineering for the 21st century, for the student century, don't think of your education as being exclusively mechanical, exclusively electrical, exclusively one. Think of being educated enough so that by working in teams with other engineers and managers, and by being effective communicators, we can solve these big human kind of problems. So I think that was the end of my presentation, Nick. I don't know how much I went over time. Maybe I did a little bit.
That's okay. We can open the floor if anybody has any questions for Dr. Lambropoulos. We have some. You can put them in the chat, or you can say them.
Oh, stop sharing.
There you go.
There. Yeah. So any questions? Any questions from the students?
Let me hop in here for just a quick moment here while we're waiting for possible questions. We're going to go ahead and if Nick, if you're good,
Yep.
We'll go ahead and we'll do our giveaway here. Okay, so let me describe what we have today. So we have mechanical engineering mugs from the U of R. These are great mugs. I use one myself. I'm also mechanical engineering faculty here. So we have a set of those. They come complete with a mechanical engineering coaster. This is actually the machine over in the Retner machine shop. For those of you who know where the Retner shop is, these are from the Retner shop. And then we have, if you're drinking a cold drink, we have these beverage holders. It's sort of a stiff plastic, and you hit it. It will wrap around your beverage so you can hold a cold beverage. So we'll be giving some of those away today. The way we're going to work this is Nick is going to give a quick quiz on some Hadrian trivia. And we will see sort of how that breaks out. I've got 5 sets of these mugs to give away. So depending on how that goes, if everyone, we'll give them to everyone, or if we can't give them to everyone, we'll sort of randomly distribute them based on the outcome of the quiz. So the people who score 2 out of 2 on the quiz will be first choice, and then so on down. So Nick, why don't you take it away with the quiz?
All right, here we go. Let's see if it worked. All right. All right, the Hadrian School is named after.
The answers to these, don't worry about that. Give it a try. Take a guess.
So everybody can do the quiz. I'm trying to click on
Yeah,
answers.
You
there
can do
you
the
go.
quiz too, I think, John. Yep.
Okay.
All right, we got 2 answers. 2 people have answered. All right, 4 out of 4.
5.
All right, we got 6 answered.
You don't have to be a
So-
student to answer. If you want to take a crack at it, it's fine. If not on campus, we will ship them to you. So we'll mail it to you.
All right, 7 out of 9. All right. All right. That looks like, I think, everybody that's voting.
Okay. All right. So the correct answers, and surprisingly, Ed Hagem actually graduated in 1958. So I remember that because that's my birth year. So he was graduating from U of R when I was born. So that will not count plus or minus for everyone. And the correct answer for the newest major there is audio and musical engineering. So since we only have 7 people there, we got 6 correct answers. I've got 5 mugs. So what we'll do is we'll randomly choose 5 out of those 6, and we'll get in contact with you and let you know. I think Nick, you've got the names, right? They come up there.
Yes.
And
If you could actually just put your email addresses in the chat, please, your name and your email addresses in the chat, just to make sure that I have everything.
okay, and then we will give out sort of the remaining people will get one of these cup holders, so everyone will go walk away with a prize today. Mechanical engineering, U of R branded, so we'll get our name out there. Thank you.
And
Has
probably
Lou
just,
joined us? Do you know?
we have Katie Ferruza is here from the
Katie,
Glenn
okay.
Green Career Center.
Okay, so Katie, why don't you take it away just real quick?
Sure. Yeah, thank you. Just really quickly, thanks for allowing me to join you. My name's Katie. I'm a career advisor at the Green Center, and you don't need to send me a mug, even though I think I got, I think I got the second question right. Yeah, so I just wanted to kind of add, it was really interesting for me to hear about some of the interests of the mechanical engineering students, et cetera. You know, just at the Green Center, we have a lot of resources available for students exploring careers and majors through Handshake. They can find internship postings. We have a variety of resources on our website and lots of different things. So students can schedule appointments with us through Handshake, drop into our collaboration hours, and connect with us in a variety of ways. And we can kind of help you think through some of these different options, find internships, research opportunities, et cetera, in addition to all the great resources that were already discussed today. So feel free to reach out with any questions. I can put my direct email in the chat as well. But yeah, I just wanted to say hello. So thank you.
All right, great. And we're going to post this too for people who weren't able to attend, especially considering the time difference. If you have questions, you can contact me at nicholas.valentino@rochester.edu. Katie will has put her information in the chat, which we will also post parts of that. Any other questions that we have potentially for Dr. Lambropoulos? Okay. Thank you all for doing this. Like I said, we have 8 more of these, 8 more different parts of the series. So feel free to join any of these. They'll be every Wednesday at 1 and Friday at 2, so that we can get our way through the Hagem School and be able to share the information about this. So thank you all for coming. And if you have any questions, I'll put some of the contact information for our participant, Dr. Lambropoulos, and we will hopefully see you on Friday.
Yep.
Take care, everybody.
Come to all, but if there are any programs you're interested in, please come and spread the word to your colleagues and friends. We appreciate it. Thank you. Take care, everyone. Thank you, John.
Bye, everybody.
Thank you for the answer that you gave on the, can my granddaughter look at this?
Oh.
I'm class of 62, chemical engineering.
Oh,
Okay.
great. Excellent.
Yep.
Yeah, no, thank you for joining us. Yeah, we're gonna put them on the Facebook page so that they can access them, and like we can help connect